Now we're going to find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 at the points 0, 1 and negative 1, 2, and we're going to write the equation of each tangent line. So let's get a picture of this. We saw this in a previous example. So here we have our function f of x equals x squared plus 1. Let's pinpoint the points 0, 1. So at this point 0, 1, if I drew in the tangent line, it would be horizontal. And let's find the point negative 1, 2. So that would probably be somewhere over here. Negative 1, maybe right here. If I drew in a tangent line to get an illustration, it looks something like this. So we're supposed to find the slopes of each of these tangent lines. So I probably could guess that this slope right here would be 0. And I could guess at least that this slope right here of the graph at this point, negative 1, 2, would be negative. And then we're going to also, after we get the slopes, write the equation of each tangent line, which means point slope. I think I'm going to start with this point first. Finding the slope at c equals negative 1. So I know it should be negative if I do all my work correctly. All right, because I have a specific x value called a c value, I'm going to use the definition of a tangent slope. So that's f prime of c, and then the equals, and then the limit as delta x goes to 0. No equals here. The equals is between the limit statement and the f prime notation. So every time we record the formula, I think it helps kind of us memorize it, since that's what we're going to have to do for tests. All right, how do I find the slope at c equals negative 1? Well, c is negative 1, so everywhere I see a c, let's replace it with negative 1. All right, at this point, if I tried to find the limit, I'd be plugging in 0 for both delta x's, but that's going to give me indeterminate. So I still have more work. I know I'm going to have delta x down here, and that's really an issue. That's what I'm trying to get rid of at the end so that I can find the limit. Okay, let's go to the numerator. Okay, this right here, this value that I need is going to come from plugging in this x value, negative 1 plus delta x, into the function. So wherever I see x, there might be multiple places. I'm going to insert for this x, negative 1 plus delta x. So I've got a square, negative 1 plus delta x. We'll replace the x. I square it, and then don't forget the plus 1. So that's the function evaluated at negative 1 plus delta x. Now I'm at the subtraction sign. Now plug in negative 1 to the function for x, square it, get 1, add 1, and that's 2. All right, at this point, if you plugged in 0 for the delta x in both spots, you're still going to end up with indeterminate. So let's do the algebra. So keep bringing the notation down, because at the end it kind of all comes together. Okay, so I'm going to have to go off to the side, and I'm going to have to distribute. So where am I going to have room? Maybe up here. Negative 1 plus delta x times itself. So whether you've learned to FOIL this, distribute, box it, whatever method for multiplying two binomials. So I'm going to get positive 1. And then I'm going to get minus a delta x, and then another minus delta x. So that'll make it be minus 2 delta x's. And then the last product will be delta x times delta x. So that's delta x squared. You could put delta x in parentheses, or you can just put a square on this symbol right here. Just remember, this square is not just on x, because this whole thing is together. So all I've done is FOIL this binomial, or distributed, and then I'm going to add 1 and subtract 2, which is just really minus 1, all over delta x. All right, I see a little cleanup I can do. The ones will cancel. Well, 1 and -1. And look at the remaining terms. All your remaining terms are likely going to have a delta x that is a common factor that we can pull up front. So keep the limit statement. I still haven't plugged in 0 for delta x. I've got a delta x in the bottom. Now in the numerator, I'm going to factor up front a delta x. So when I divide delta x out from this term, I get -2. You can always check by multiplying it back in to see if you get what you had. And then delta x divided out of delta x squared just leaves a delta x. So again, you can just distribute it back in and do a quick mental check that you factored correctly. The reason you want to pull that delta x up front is so that it conveniently takes care of that issue in the denominator. So coming back over here to the left, f prime of -1 equals, I am ready to plug in 0 for delta x, so that means I'll lose the limit statement, it goes away. When this gets to be 0, then my answer is -2. So let's go back and look. We expected that the answer should be negative because this graph of f is decreasing through this point, so we should have a negative rate of change, a negative slope, etc. So going back to the directions, I did find the slope of the tangent line at this point, but now I've got to write an equation for this line. So that's going to be our point slope formula. So that's y minus y sub 1 equals m times quantity x minus x sub 1. So if we come up here and label this point, this is our x sub 1 and our y sub 1. So then coming back here, we're going to do y minus 2 equals, now remember, this is our slope, so our derivative is our slope, or gives us our tangent slope, so that's -2, parentheses, and then x minus a -1, which will be x plus 1. So this is what we call a safe stop. You can stop here unless you want to solve it for y equals. All right, now let's tackle this part of the problem right here, where it looks to me like my slope's going to be 0, so I'm expecting a 0 answer. Okay, and if I wanted to, I can actually write the equation of this tangent line without doing any work. If I'm expecting that the slope is 0, then this line right here passes through y equals 1. So at the end, when I'm finished, I should not only get a slope of 0, but an equation of a tangent line that's y equals 1. All right, so let's go ahead and first look at finding the slope. So I have a specific x value, so I'm going to use the definition of a tangent slope. Okay, next line, I know what my c value is, it's 0. Remember, the equals is right here before the limit, not in between the limit statement and the fraction. You can clean this up. That's just delta x. Actually, I'm going to save myself a line because I might run out of room. Okay, so next thing for me is I'm going to plug in, I don't need to plug in 0 plus delta x because that's just 0. I need to plug in delta x for the x in the function. So delta x squared plus 1. Again, you can put parentheses around that if that, that feels better. So it's delta x squared plus 1 minus f of 0. So plug in 0 and you just get 1. I see that plus 1 minus 1 will cancel. I haven't plugged in 0 for delta x yet, so that's why the limit's still there. And oops, I forgot the delta x here. So I've got delta x squared on top and then a delta x down here. If I plugged in 0 for delta x, I get indeterminate. So let's divide out a delta x with one of the ones that are on top. So now I've got f prime of 0. The slope of f at 0 is equal to All I have left is just a delta x, so when I plug in 0, my answer is going to be 0. Just what we thought, because we did feel like the slope of f at x equals 0 would be 0, because it's a horizontal line. All right, then to write the equation of that line, if you want to go through all the work, you don't have to, but if you see the equation of that line would be y equals 1, because you pass through a y coordinate of 1, you can go straight to there. Otherwise, using the point slope formula, we'll verify that we get y equals 1. Okay, so for this formula, if we're using this point, this is our x sub 1, y sub 1. So it'd be y minus 1 equals, m is your slope, and that comes from the derivative, so that's 0. It comes from the prime equation, x minus 0 here. And 0 times anything is 0, so you end up with y minus 1 equals 0. And if you wanted to add the 1 to the other side, I probably would. We're going to get the equation of the horizontal tangent line to be y equals 1. Okay, so for the next example, it says find the derivative of this function that we've been working with by the limit process, or the definition of a derivative. So that's the other formula that was on the previous page. So we've been using this formula because we knew what c was, but now we don't know what x we're talking about. So what we're going to do is we're going to use this formula right here. So we'll do that first, and then we'll come back and use this derivative, which will be another equation, to verify what we found up here. Nope, not f prime of c. We don't know what c is. We're talking about at any x, because it'd be so tedious to do this process for an infinite number of x's. We need a more efficient way to find the slope of every single point on this graph, as opposed to doing what we did here. And that's the intent of the derivative. So similar formula, just all c's are now x's. Okay, I don't have anything to replace in for x. So we kind of skip that step. Okay, but I do need to plug in something for f of x plus delta x and f of x. Well, behind this subtraction sign, I'm going to be putting in actually the equation x squared plus 1 here, but I need something up front here in front of the subtraction sign. So I'm going to come over here and do a little side work. So here's the function that we want to find the derivative of. So, and we need to figure out what expression represents the function evaluated at x plus delta x. So that's my input, that's my x value. It's going to go in this spot. So we'll want to square x plus delta x. And then we don't want to forget the plus 1. Okay, so now coming back over here, I'm going to insert quantity x plus delta x squared plus 1. I'm at the subtraction sign. Now the function I'm subtracting is x squared plus 1, but make sure and put it in parentheses so that negative gets distributed through both terms. That's not a problem to put parentheses around this if there's just one term, but if you have more than one term, then that negative has to be distributed through. Okay, we need to go off to the side, and we need to multiply x plus delta x. So using our distribution skills, FOIL, boxing, whatever method we learn, x times x is x squared. X times delta x is 1x delta x. A lot of students make mistakes right here, so just kind of watch out for that. That's x delta x. Plus, now on the inside, that's another x delta x. And the two last terms multiplied is delta x squared, with or without parentheses. Now these are like terms, so we'll put those together. So x squared plus not just one, but another one, 2 of the x delta x terms plus delta x squared. So I'm going to come back over here, and I'm going to insert x squared plus 2x delta x plus delta x squared, and that just came from multiplying this binomial, plus 1, distribute the minus, minus x squared minus 1, all over delta x. Again, you can try and plug in 0 for all the delta x's, but you're going to get indeterminate. We still have more work. So keep the limit while we do our cleanup. Okay, what should happen is things should cancel. If your function doesn't cancel with something up front, then we made a mistake. It's like a built-in flag. So minus x squared and x squared cancels. Minus 1 cancels with the 1. All remaining terms are we add or subtract, should have a delta x in them. So this is what's left. Let's go ahead and take that delta x factor, that greatest common factor, that GCF, out. So dividing delta x out leaves 2x, plus taking a delta x out here, from 2 of them leaves a delta x, all over delta x. And again, the benefit of that is these delta x terms will divide out, bring down f prime of x. The limit statement won't come down because you're about to plug in 0 for the delta x, not the x, and your final answer is 2x. Notice it's not a value, it's not a slope, because we weren't talking about a specific point on the graph. So this is a derivative. Yay. We just derived this function. We found, no, notice this is f of x. That's the original function, f of x. The prime that goes with this specific function, the prime, f prime of x, also known as the derivative, is a slope formula. It's an equation that we can plug an x value into to get the slope on the f graph at any x. So let's verify the slopes from above. Where am I going to do that? Okay, over here. Verify slopes from above. Meaning use this derivative we found, f prime of x, to verify the slopes of 0 and what was it, -2? So at the point x equals 0, 1, at x equals 0, if I plugged in 0 for the derivative for all the x's, it'd be 2 times 0, so f prime of 0 is 0. And that's what we found from above. Oops. So how about at the x coordinate of -1, when that point was -1, 2, use the derivative attached to this function, f prime of x, plug in -1, it's 2 times -1. I'm just plugging in the x values to the derivative, and the slope is -2. Also, you might have forgotten, but on the front page, when we were doing the exploration, I was still working with the same function, x squared plus 1, and you were given that the slope at x equals 2 is 4. So if we look over here, if we plug in 2 for this x and 2 for that x, f prime at 2 would be 4. So we found the derivative correctly. Okay, more of the same, but the functions get a little more complicated, so we need some strategies for like the cleanup of it. All right, so for this example, we're dealing with the cubic now, a third degree function, a cubic. Find the derivative, use the definition of the derivative. Every time we write down the formula, hopefully we can internalize it for when we have to recreate it. Okay, so what's the prime equation related to this particular function? Every function has its own unique derivative. We have to just go through this process of finding the prime for this given function. So notice we're just asked to find the derivative. We're not asked to find the slope on this graph at any point. So once we get the derivative, we'll be done. And that's going to be enough for this problem. Okay, my input value is x plus delta x, and notice in the equation for f, we're going to have to insert x plus delta x for this x and for this x. So we've got x plus delta x cubed plus 2 times x plus delta x. And we're at the subtraction sign minus the function, so the function is x cubed plus 2x. Be sure to put it in parentheses so you can distribute the negative. Okay, we're not going to go beyond a cubic because this can get very, very tedious right here with the algebra. But in order for us to cube this, we're going to have to multiply 2 of them together first, get that answer, and then multiply that answer by the third parenthesis. So we're going to cube it. Let's multiply 2 together. And from the previous problem we did, this is actually x squared plus 2x delta x plus delta x squared. So we found that in the previous example. Then let's take this answer and multiply it by the third parenthesis, x plus delta x. So I think I'm going to have to bring this down here. So let's take x and multiply it by these 3 terms, and then take delta x and multiply it by these 3 terms. So x times x squared is x cubed plus x times 2x delta x. Well, that's going to keep the 2. X times x is x squared, and we only have a delta x. X times delta x squared is going to be 1x with the delta x being squared. Then take delta x and multiply it by x squared. So that's x squared times delta x. Delta x times this term would be 2x with delta x squared. So 2x delta x squared, and I still ran out of room. And then delta x times delta x squared is a delta x cubed. And let's notice that this term, 2x squared delta x, matches x squared delta x. The x has the same exponent of a square, and then they each have a delta x. And then this term, x delta x squared, will match x delta x squared here. So we'll collect them. So coming back over here in the numerator, we're going to have x cubed. And then I'm going to add here, and I'm going to get 3x squared delta x terms. Add the blue ones, so plus 3x delta x squared. And then finally, plus delta x cubed. Notice that's just from cubing this binomial. So now we're here, so let's distribute the 2. So plus 2x plus just 2 delta x. Distribute the negative 1, minus x cubed minus 2x, all over delta x. If you tried to plug in 0 for the delta x's, not the x's, you'd still get indeterminate, so we still have more cleanup. All right, let's see what cancels. We should be able to cancel the function. So x cubed and x cubed will cancel. Well, that's a minus. Minus 2x, and there should be a positive. There it is. All remaining terms should have a delta x in it. So we've got 1, 2, 3, 4 terms with the delta x. Let's pull that up front. So just be careful when you divide it out. Dividing it out leaves 3x squared plus, when you pull a delta x factor out, you still have 1 left, so you've got 3x and a delta x, plus dividing out a delta x gives delta x squared. Dividing out a delta x will leave the plus 2. Again, I encourage you to distribute that delta x back through to make sure you end up with what you had here. These will divide out. We should be close. So f prime of x, the derivative is equal to, plug in 0 for the delta x's. So that whole term will go to 0. Delta x being 0, that term will go to 0. Look what's left. We've got 3x squared and a plus 2. Yep, that's right. So that is our derivative. Just now looking at the key, and I have a mistake on that. I think I lost my plus 2. I have to reload that key. Yeah, that should be 3x squared plus 2. Oh my goodness. So this is our derivative. We've just derived this equation. This is what I sometimes call, it's called many things, derivative, slope formula. This equation will give us the slope to any x value on this graph. If I'm interested in what's the slope at x equals 2, I'd plug in 2. If I'm interested in the slope on this graph at x equals 3, I would find f prime of 3 by plugging 3 in here to get the slope. Okay, just moving on, looking at some other examples that present other algebraic opportunities. Okay. All right, let's find f prime of x. Notice that up here they use the language find the derivative. Here they're just saying find f prime of x. So we just have to know it's the same formula, whether they use words or notation. So let's find the prime for f of x equals square root of x minus 2. Now the minus 2 is not underneath the radical. So we'll find that first, and then we'll come back and then complete the rest of the problem. Strictly the formula. Now let's customize the formula with my function. Okay, we want to put in x plus delta x for this x underneath the radical. So I'll have the square root of x plus delta x, and then I still have the minus 2 part, minus parentheses the function square root of x minus 2 over delta x. Goodness, I'm looking at this. I think I am so sorry. This radical needed to be all the way over x minus 2. So let me adjust that. Yeah, that's not the one I wanted to do. This is the one I wanted to do. So if that radical's all the way over x minus 2, then it should be x plus delta x, and then this should be underneath. Minus, and I won't need the parenthesis here because it's just the square root of x minus 2. Yeah, that's the one I wanted to do. The other one would have probably been too easy. Okay, if we plug in 0 for the delta x here and here, we're still going to get indeterminate more work, but notice that unlike up here where we could multiply things out and factor, okay, we don't have that situation here. Okay, we're actually, the strategy with square roots is to multiply by the conjugate. So right here in the problem, I'm going to tack on a multiplication of a form of 1. And that form of 1 is going to involve the conjugate of the numerator. So when I look at this, I can think of this as two terms being subtracted. Let me change minus to plus, and that is producing the conjugate for the numerator. So square root of x plus delta x minus 2, all underneath radical, plus square root of x minus 2. So same terms, front and back, only change the operation. So in the denominator, do the same thing. We want to populate the denominator with that conjugate as well. That's a form of 1. Seems a little tricky at first, but it worked out okay. So we're actually going to end up multiplying these two together. So let's come down here, f prime of x. Okay, when I multiply two conjugates, instead of foiling, okay, I could do that, but I won't need to. Some things are going to cancel. Let's multiply these two terms together. They're the same radical. So a radical times itself is going to give us what's underneath the radical. So the radical will disappear when I multiply, and I'll have x plus delta x minus 2. And then I have a minus times a plus, so that's minus. And I just have to multiply these last two, no outside or inside terms. So multiplying these two together, same radical, gives x minus 2, but make sure you put that in parentheses, or you at least distribute the negative. Okay, let's clean that up a bit. I got x plus delta x minus 2 minus that x, I'm at the distribution, minus x plus 2 over delta x. Okay, so we multiplied by the conjugate when we saw square roots. Just be careful. Oh, goodness, what's going on with me? Okay, I need to multiply these two denominators together, but I'm not. I'm just going to leave the delta x out in front of this denominator. Getting in a rush with the video limits. Okay, so multiply these two together, but don't multiply that delta x inside, because our ultimate objective is to divide that delta x out with another delta x on the top. So let me re-record this denominator. Was that plus square root of x minus 2? Yeah. Yep. All right, now on top, the 2, well, minus 2 plus 2 minus x. So what we have is just a delta x on top, but I can divide that out. There's a lot of work in one step. Probably not recommended, but I'm running out of room. This delta x will divide out of itself one time with that one right there. So let me come over here. Still have the limit. Okay, so the only thing left on top is a 1, and I need a little placeholder there. The delta x is divided out, and so what I have on the bottom is the square root of x plus delta x minus 2 plus square root of x minus 2. Now let's plug in 0 so we can lose the limit statement. So I end up with f prime of x equals, the limit's gone because I'm plugging in 0, 1 over, that's going to be a square root of x minus 2. That goes to 0, so I'm left with x minus 2 plus another square root of x minus 2. And finally, the last cleanup is, let's collect these two like radicals. There's 2 of them, so 1 over 2 radical x minus 2. All right, but going back to the question, we're not done. It says find the derivative, and that's all we did. We noticed we had square roots. We multiplied by the conjugate. I was trying to be careful, but kind of failed there for a minute. We got the derivative. Then find the slopes of the graph of this function at 3, 1, and then the other point 6, 2, and write the equations. Goodness, I think I'm going to have to come up here. So let me first tackle the point 3, 1. So this is x1, y1. So the first thing we need is the slope, and the derivative will give us the slope. So let's plug in 3, the x coordinate, not the y, f prime of 3 for the x and the derivative. So I'm going to come up here. So the slope of the graph, this graph at x equals 3 is equal to 1 over, well, that's just 1, square 1 is 1, 1/2. So remember, this is m, the slope. So now let's use point slope to write the equation of the tangent line at that point 3, 1. So we've got y minus 1 equals, m is the 1/2, insert that, x minus 3. And that's a safe stop. And just looking at the time on this video, I'm not going to have time to do 6-2, but if you look at the key online, that will have that one completed. I don't know how I had more room there than I do here because I'm writing pretty small. So in the next video, we'll just pick up this example right here.